Good morning. I hope you're doing well. I am doing very well. I'm a little bit cold. The temperature has definitely plummeted pretty recently in Melbourne, and yeah, I am feeling it. But other than that, I'm doing very, very well. I'm very excited to share with you what I've been up to for the last week. It could have been the last 2 weeks, but I ended up just being really busy with other stuff, and I didn't really do anything on Jugglebot last week, like the week before this week. But I was able to get a lot done this week, and I'm very keen to show you what I've been doing. It's mostly good news. I mean, there's not really any bad news. It's just kind of like meh news, but it's mostly good, which is obviously a good thing. So yes, the title is that the orientation calibration is finally working. I realized that my title and everything of the last live stream that I had, I should probably update that because I only realized after the fact that back then I was only able to get the position correct. So we could command Jugglebot to go to a given position as long as it was on this plane, and it would get there fairly accurately. But I had not even checked the angles, the orientation of Jugglebot in any of those poses. So 2 weeks ago was a little bit disingenuous, and I'm not a big fan of doing that. I am a big believer in being honest about what the technology that you're working on can do. Got a lot to say about that, but that's probably a conversation for another time. But yes, I will probably update that after this stream actually. So I don't like that was a bit disingenuous. But now orientation calibration is actually working. So now we can get the position and the orientation. So we can get a full 6-degree freedom pose that we command Jugglebot to, and it gets there pretty damn accurately. And we'll see what that looks like in a sec. We've got lots of demos today. It's very exciting. I'm selected on the wrong screen. Okay, but first off, we again have a kind of fun tangential thought this week. It's not a normal one, but it's one that I've been, I don't know, thinking about for a little while and have finally decided to actually begin the process of sharing this, which is that I've mentioned a couple times that one of the big goals of this project, the main goal that I kind of like keep coming back to when I'm, I don't know, in the dumps about how things are going, is to have a huge number of Jugglebots, like 100, say, juggling an absurd number of balls between them in time to music, and having different patterns appear and disappear as the music, I don't know, like in sync with the music, so it all kind of like fits together nicely. But I've never actually shared any of the songs that I think would be good for this, and because I only started keeping this list a couple of days ago, I only have 3 songs on there right now. But it's interesting. I'm sure everyone's experienced this with music, where you like when you find a song that you really like, you listen to it tons, and then after like some period of time, you go, nah, I don't love this anymore. So I've had a lot of songs in the past where I've been like, this would be an amazing Jugglebot song, and then now I listen to it, and I'm like, nah, I've listened to it too many times. So these are just kind of like my ones that I'm currently listening to that I think are quite good. First is Arrival by Cream. The whole song, just fantastic. It's a banger. Heaven Listen by Weevil, at least the first minute of it. As soon as the guy starts making whatever sounds you would call that, don't love it. Gets a little bit less cool. And then the last one is All Melody by Nils Fram, which there are a lot of Nils, I don't know how to say his last name, Fram or Frame? Fram. There are a lot of his songs that I think would be fantastic for Jugglebot. It'd be very, very cool. So yeah, I definitely recommend checking these out, and I'm intending to make a topic on Zulip about this. So if you have songs that you think are in this kind of, I don't know, vibe, then I would love to hear them, because I'm always on the lookout for more juggling songs, especially ones that are good for Jugglebot, which I don't know how to describe the differences between songs that are good for me juggling and songs that are good for Jugglebot juggling. There is definitely a difference between them, but I don't know how to describe it. But maybe you can get the idea from this one. Arrival is definitely the peak one for me right now. It'll be so good. Definitely recommend listening to those. Okay, so let's get into the juicy bits. How to calibrate for orientation. The way that actually before I go into any of this, I think it's worth I don't know, addressing where we were at 2 weeks ago in the last stream, where we had a couple of different options for how to move forward. So last week I had a grid of 100 points, and I basically commanded Jugglebot to move to all of those points, and then I measured where it was actually at using the motion capture cameras that I've got, and then we can use that measurement against the commanded position to figure out how much error there was, and then in the future, whenever we're commanding Jugglebot to move to a position that's near one of those, I was doing it a very crude way before, where I just grabbed whatever the nearest pose was in the calibration set, and then said, okay, when we were commanded to that position, we had this much error. So let's just subtract that much error from where we're now commanding Jugglebot to go to, and that should get us pretty close. And it actually did. It was surprisingly good, I thought. But we had a couple different ways to move forward from that. So we could either, one option was to change the number of points that we had in the grid to have like a kind of finer resolution for when we're sending out future commands. Or we could also have the same number or even fewer points and sample between multiple like calibration positions or poses. And there were also at that point we were only looking at positions as well. We weren't doing any orientation stuff. So we needed some way to include these orientations into this calibration set. And I was a little bit unsure of how to do this because there's different demands on Jugglebot based on if it's going to be juggling to itself or if it's going to be juggling with me. And if it's going to be juggling with itself, then it only ever needs to angle towards its like center line. It's going to be very, very uncommon, probably never going to happen. Like, I mean, it's going to be very, very uncommon that it is juggling with itself and it's pointing like away from its center line. Because if it angles away from its center line and throws the ball, then the ball's probably going to land outside of its workspace and then it can't juggle with itself anymore. So if it's with itself, it just needs to angle in. But if it's juggling with me, then it needs to do pretty much, well, not the opposite. It doesn't always go outside away from its center line, but it will occasionally. And I really want it to be able to juggle with me. So I want to keep our options open for now. And then if this doesn't work, then we can narrow in on just juggling with itself. And then we can only calibrate for those angled in poses. So what I did is I kept the same grid, which is a 360 by 360 millimeter square. And that's like full side length. So like the center point is at like 180, 180, if you want to think about it that way. And there's 100 points in that grid. So there's 10 along each side. And then I've added a plus or minus 5 degree and plus or minus 10 degree roll and pitch angle at every single one of these poses. Every single one of these points. I did not really pay enough attention to how I was setting this up, and I wasn't really thinking about it too carefully as I was getting this configured. Because I didn't realize that this would also, the way that I had set it up, also added these angles in combination, which is probably a good thing in reality, because it means that rather than just going to one side or the other side, we're actually going at like a 45-degree angle, which is probably a good thing. But it means that the number of poses that I'm creating here is huge. And I ended up with 2,500 total poses, which is a lot more than 100. And I did not really appreciate how long this would take to run. It took well over 2 hours. It was probably closer to like 2.5, maybe even 3, maybe not 3. It's probably 3 hours like in total from the very start of when I began to when I ended, because I had to do a bit of stuffing around. Because, unfortunately, leg 4 became a bit tired after around 450 poses. So I set this thing going. It was going to a pose. Again, just to clarify the way that I'm doing this now, is that Jugglebot receives a commanded pose. It moves there. It waits until all of the legs have stopped moving. So all of the O drives that are controlling the legs they report the position and the velocity of the motor. And when the motor velocity is below a certain threshold and the position is where we want it to be, then we say that that leg has stopped moving. And when all of the legs have stopped moving, we say, yep, the platform is still. We then wait another half a second or a second or something like that. And then we take a snapshot of what the motion capture cameras are reading, and then we can compare that against the commanded pose. So that's kind of like where we ended up. Obviously, this is not how things will be able to work when Jugglebot's actually juggling, because it'll need to be moving around a lot more dynamically, but you've got to start somewhere. So yeah, it was moving around, and it got through about 450 poses, but then leg 4 became tired. And I don't know how else to describe this, but it's something that I have observed in the past before as well, and I believe I've mentioned on here, where for some reason, it seems like it's more often than not leg 4, so it's probably something hardware related for that linear actuator, but I don't know for sure. But what I mean by tired is that I'll send a command position for that motor, and it will just take a long time to get there. And like, even if it does get there, it'll kind of like very weakly hold its position there. So it doesn't like settle down as quickly as the other ones do. Like all of the other legs will go out and then stop, and they just hold their position. But leg 4 will just take its time. It'll get there, but slowly. And sometimes it just like wouldn't even go at all, and I would have to actually like go manually and like give it a nudge to like kind of get it started. It was very weird, and yeah, I don't really know what caused that, but one thing that is worth noting is that it hadn't been run in almost 2 weeks, so it's possible that something related to that was an issue. What I mean by hadn't been run is that like it was completely powered off and like hadn't even been moved in almost 2 weeks. So yeah, I don't really know what the problem there was. I really wanted to show you what I mean by tired, because it was behaving this way up until this morning. Like, yeah, I think it's to do with how much I use it. If I use it, or if enough time passes, then this leg just becomes this way. And I really wanted to show you this, but I was unable to because I needed to get some data for something that I'm going to show you a little bit later. But yeah, I think my description was pretty accurate. It just takes a long time to get to where it's going to. Thankfully, it's a very easy fix. I can just rerun the full calibration sequence. And of course, I probably didn't need to do this on all of the legs because all of the other legs seemed to be responding very snappily. But I just did it on all of them anyway, because I'm like, oh, I've got another 2,000 poses to go. I don't really want to have to be like, I don't know, aware. I don't want that to be a problem if it will be. So I just did it on all of them, and then redid the. I then started at around 450 poses because I didn't want to have to do them all again because it was taking a lot longer than I was expecting it to. But then I just merged the two files at the end and ended up with the full 2,500. However, I had to cut down some because in some of the poses, some of the legs were over or underextended. And what this means is that when we command the platform to go to that certain spot, it gets as close as it can, but it's not going. There are very low level like security. Well, there is a very low level security layer that I've added to this, where right before we send the commands out for the motors to move, we just do one last final check to make sure that it's actually within the physical allowable bounds of the actuators. And this is because this step is only right at the very end. It's a little bit annoying to, like, I definitely could pre-calculate this, but it's a little bit annoying to calculate in advance whether or not a given pose is going to be reachable or not. So some number of the poses, what is it, 326, if I can do math. Some number of poses had one or more legs being too long or too short, and so those poses were perfectly valid to send to the robot, but of course if it tries to move there, it's not going to get close because the legs are not the right length. And so we don't really want those poses in our calibration set because it's not like an earnest attempt of the robot to get to that position. It's getting as close as it physically can, but it's not physically able to give it like the old college try, you know? So yeah, after removing all of those poses that it can't actually reach, we ended up with 2,174. Which is quite a lot. It's definitely a heck of a lot more than the 100. And since there's so many poses, you would think that it would take a long time to search through these, so that when we're actually using this in real time, it might take a long time to search through these 2,000 plus poses to get the nearest one to where we're going to then find what error we need to apply to where we're trying to move to. And thankfully, like, if I was doing this the way that I was doing it last week, then yes, this would not run very fast at all, I would expect. And it probably wouldn't even be that good because I was only grabbing the nearest pose and taking that error as the error that I'm going to now, even though now I'm not actually going to that specific pose. So I wanted a faster way and a better way to do this. And in case you haven't been playing around with ChatGPT recently, it's getting very, very good. Just one quick little aside on something I found interesting about ChatGPT is the O3 model is it feels significantly smarter than any previous model, and something that I think is quite interesting, that is not really an indication of like intelligence per se, but it's just like an interesting note, is that it has started signing itself as the author in the Python scripts that it generates for me. It was never doing this in the past. It would always just like spit out the code and then say, here you go. But now, right at the top, in that top like comment block, it's got author ChatGPT 03 month, year, I believe, or maybe just year. It's interesting. And for the ones so far, I've been like, nah, delete that. But I don't know if I'm going to always delete that. I think it's it's definitely the majority author of them, so I might keep it around. But in any event, ChatGPT was able to suggest and create and refine code for me to generate a KD tree, which I don't really understand the nitty-gritty of too well, but I can describe the general process. So the idea here is that if you have some number of like calibration, I'm taking my case in particular. If we have these calibration positions like this, so we've got like X down here and Y here. So this is our plane this is obviously just XY positions. In fact, we have orientations as well, but let's ignore that. If we have these positions, what I was doing before is I was saying, okay, we want to move to this position here. What is the nearest one? Well, how do we know? Well, what we can do is we can search and find the distance to every single one of these points, and then take the smallest distance, and then we say, okay, cool, that's the smallest distance. That's obviously not a very efficient way to do things, but it's what I was doing last time, and it worked pretty okay. But now, with the KD tree, rather than having to search through every single point, what it does is before we even when we generate this data set in the first place, it splits up this information into a tree format, where it basically divides this is not a very nice layout. It basically divides your data into two sets, say along the X direction first, and then it will divide the data along the Y direction. So on this left-hand side, let's say we have another data point here, we might divide it this way, and then on the right-hand side, let's just put a couple more points in, it might divide it here. And then it continues dividing. So if in each of these sections, it divides again and again and again along the X direction, and then we divide along in the Y direction with whatever's left. And what you end up with is you have this like network of divisions that you can kind of search through. So you can say, okay, like at the very top level, here was our first line. Am I on the left-hand side or the right-hand side of this line? If we're on the left-hand side, then we only need to look at these guys. And now we say, okay, I'm on the top half of this line or the bottom half of this line. Okay, I'm on the top half, so I only need to look at these two. I'm on the left-hand side of this line or the right-hand side of this line. And it means that you can just like, whoop, you can hone in to the closest point really quickly. That's about the limit of my understanding of this. There is a library in Python that does this for you, and there is a ChatGPT that uses the library for you. So nowadays, you don't really need to get into the nitty-gritty too much. If you are curious about how I've implemented this, I have a link in the description for the code, is generate KD tree. Yes, I just remembered something I wanted to mention earlier, but I'll say it later if I remember. So, yeah, you might be wondering, okay, this is still searching through 2,100 poses. Like, surely this is still going to take a while to run. But it actually doesn't. It's usually around 2 to 3 milliseconds. There have been a couple instances where it takes like 20 milliseconds, and I don't really know what is causing that to happen. I'm kind of suspicious that that's like real data. The way that I'm getting the report of like how long this is taking is that at the end of every ROS session, if there have been any cases where I've been using this like feed forward correction, then it will spit out a summary at the very end of the session. It will say what the average number of milliseconds for like applying that correction takes, and what the maximum is, and the standard deviation. And the mean is usually 1 to 3 milliseconds, but sometimes the max has been like, yeah, upwards, like around 20 milliseconds or so. And the reason why I'm a little bit skeptical about whether that's like real or not is because I believe that was when I was getting Jugglebot to move outside of the plane that I've kind of calibrated in. So I've calibrated everything so far to be on one like Z height, just because I think that that will be all that's necessary to get Jugglebot to juggle at all. We can play around with other Z heights a bit later. A bit later, probably. But when I was like controlling with the space mouse, for example, I was getting it to go up and down in all sorts of different directions. So it's possible that when it's trying to figure out the offset for poses that are well outside of the calibration plane, it might take significantly longer, maybe. But in general, it's very fast, and I should be able to run this at 100 Hertz, which would be pretty damn good. And not only is it fast, well, fast-ish, it's not actually faster than what I was doing last week, but it's fast-ish, it's fast enough. It is also, rather than just grabbing the nearest point in our KD tree and saying, yeah, that's the point, let's take that error, it's actually weighting the error from the nearest 8 neighbors. And I can configure this in my code to be fewer or more neighbors, and perhaps that would affect how long this calculation is taking. That's probably worth playing around with. But in any event, it's weighing the error from the nearest 8. So it should give a much more reliable indication of what the error is actually going to be at the position that we are, or at the pose that we're being commanded to. So it's very good. And I can also toggle whether or not to apply this feed-forward correction with a ROS2 parameter while the ROS session is going. So I can do some sequence of moves with the correction on, and then I can do the exact same sequence of moves with the correction off without having to turn anything on or off, and like without having to end the session. And it's, yeah, very convenient, very nice. But the big question is, does it work? So yeah, it would obviously be, I don't know, not very useful if it didn't work. So what I, again, had ChatGPT make is a script that takes in a recording of the ROS session and then plots these, like the calibration recording, so it looks at the commanded positions against the measured positions, and it plots the various errors that we have. So this is with the feed-forward correction off, and yeah, I'll just go, my description here of 90 out of 94 bad is that 90 poses out of the 94 that I sent it to were quote-unquote bad. And what that means is that the position error was greater than 10 millimeters, or the orientation error was greater than 1.5 degrees. And I would consider both of those poses as being, well, both of those error margins as being bad, because it's pretty likely that that's going to cause either a really erroneous throw or a failed catch. 10 millimeters might be a bit narrow there. It can probably go to a bit bigger than 10 millimeters error, but I had to put the limit somewhere. Also, these poses, just for reference, are 100 randomly generated poses within a 360 by 360 square with angles up to, I believe, 10 or 15 degrees. I can just quickly check that. It was... Where did I write it? Oh, 10 degrees. Yes. Pretty... it's a bit messy. 10 or 15 degrees. Yeah, it's going to take me a sec to find where I wrote that. But yeah, it's 100 randomly generated poses. And we can see up the top, we've got the position distribution, so where all those poses were. And you can see based on the color of those points, what the error at those positions was. So it is interesting that we can kind of, there's more error down on the right-hand side where X is larger, which is interesting. But then down the bottom, we can also see like the, what are these called? Like the count, the histogram of what those errors were. And yeah, there's a lot of big errors, especially around the roll. And for some reason, the Y axis has a lot of error, a lot more than the other two. But that's with the feed forward off. What about with it on? Well, once we turn it on, let me get rid of me. We see that we know we have 0 bad poses now. So not a single pose in this 100, what was 100 poses, but is now 94 because we chopped out the 6 that had the legs being too long or too short. Same thing as here, it just happened to be 6 poses again that were too long or too short. You can see that these are different poses. I was considering making this so that the 100 randomly generated poses would be the same poses for the feed forward off and the feed forward on. That feels like that would give the, I don't know, best reflection of how much of a difference this feed forward actually makes. But I was only doing this like an hour ago and I wanted to just get it done before the stream starts. So the easiest option was just to randomly generate every single time. So they are a bit different. But I feel that the 94 poses should be pretty representative of the whole area. And like, it looks like there's a decent spread over the whole thing. Interestingly, the error seems a lot more dispersed in the feed forward on case. There's kind of regions, like points with large error kind of all throughout the grid. They're not just on the right hand side, which is interesting. That kind of lines up with what we saw 2 weeks ago when we had the position offset, where prior to the calibration being applied, we had this really, it was kind of like two perfectly parametric curves of error, basically, as like the further, it feels like we could kind of fit. I think actually someone suggested this in a comment. That I've been really bad with replying to comments in the last 2 weeks. I apologize. I'm going to try to reply a bit sooner, but other stuff just gets in the way. But I believe someone actually suggested that we can potentially, if we fit enough points, if we have enough calibration points, we might actually be able to find like a parametric equation that describes what the error will be based on where we're moving to. It's a very interesting idea, fitting to that curve. And this kind of, but then once we applied the correction factor, that curve just like disappeared. It looked like it was just kind of random noise after that. And this feels very similar to that. So we've got a general trend where the further right we move, the more error we have when the feed forward is off. But then when the feed forward is on, we kind of got a spattering of errors everywhere. And we can see in the histograms that everything is a lot more tight. So before, where the Y error was kind of spread out between -5 to 7.5 millimeters, the whole thing is between, what, 4 and 7 millimeters? And same thing with the X and Y. Like you can see they've just like really tightened up. The Z is the Z and X. The Z is definitely the closest. It's very good. I don't know why the Y is off. I have a suspicion that actually might be to do with the motion capture system. Like I think that my origin of the platform might not be spot on where the actual origin is potentially. But in any event, it's still significantly better. Like that, this whole spike is like here to here. So it's definitely a lot tighter than before. And the rotational errors are like, it's not even close to how much better that is. Like 0.4 to -0.8 degrees. That is so good. I'm very, very, very happy with that. However, there's something that's worth noting with this, which is that this, how can I describe this? This morning, so I mentioned earlier that leg 4 was feeling a bit sleepy again recently, and I wanted to show you what this looks like, but I was unable to because I had to collect data. This was the data that I had to collect because I first ran this feed forward on process with the leg 4 being tired, and I wanted to do the feed forward on and the feed forward off with leg 4 being tired, so then I can still show you what that looks like. But unfortunately, when I was doing the feed forward off, the leg 4 just kind of gave up. It got a spin out error and yeah, just gave up. So I had to rerun the full calibration sequence. That got rid of the error, and then I was able to do this recording. But I still have the recording of when the feed forward was on, but leg 4 was being tired. And I think it's very interesting to see because the errors are significantly bigger. It's a lot better than when the feed forward is off. So you can see when the feed forward is off, we have 90 bad poses out of 94. But when the feed forward is on with the tired leg, we have 52 out of 96, which is a heck of a lot worse than 0, but it's a lot better than 90, whatever it was, 90, yeah. And we can see a similar kind of thing. So even though the leg is tired, we still have this kind of like clumping together. So everything is a lot more tight, but the errors are just way larger than when the leg is not sleepy or not tired. So yeah, it's obviously, like the feed forward is obviously helping quite a lot, in my opinion. Well, from what I can gather from the data, but it's also very important that all of the legs are responding quickly and are not tired, whatever the heck that actually physically means. Like I've got no clue what is actually physically going on here to make this effect, which is why I'm using such a vague term as tired. if anyone's got any ideas, I would obviously be, yeah, I'm very open to them. But yeah, I don't know. In my mind, this just means that maybe I can have like a sequence where before doing like a big, I don't know, session, I can have it go through like some kind of calibration sequence, and then it tells me, hey, like the calibration's not perfect. You should full calibration sequence all of the legs. And so far, I've been doing this like full calibration sequence just manually, just over USB. I plug it in, I go on the ODrive tool on the website, or the GUI, and then do them one at a time. Perhaps it's worth me, it probably is actually worth me putting this into the ROS network so that maybe I can just do this once every day. Every day I just get all of the legs to go through their full calibration sequence, and then that should completely remove any like tired leg problems. It's just such a weird problem. I don't know. It does... I can't help but be reminded of a story that John shared on Zulip sometime in the last month, where he was talking about a project that he was working on where there was a motor that was supposed to be stationary, like they had commanded it to be stationary, but it was moving at like some absurdly slow rate. It was like 1 degree per hour or something like that. And the problem that was causing that was that there was a rounding issue, essentially, where there was a number that was supposed to be like 0, but it was ever so slightly off. And like that kind of, there's a term for this that I'm blanking on right now, but basically, like, I think floating point error is the right phrase, where you just have like these tiny little rounding issues, and they just add up ever so slowly, and they add up in the background. Because these are like 1 times 10 to the negative 16, like significance, it takes a long time for these to kind of build up to be any kind of appreciable amount, but they do eventually, and then they cause problems. So it could be something to do with that. There could be some kind of floating point error going on in that O drive, but it's not going on in any of the other O drives. I don't know. But yeah, I should probably include a calibration routine to get the legs to go through that every time. But yes, a good thing that I discovered, well, actually, yeah, just to wrap this up, I am a big believer that the feedforward on has improved things a lot. It is possible, like I have not tried what John suggested last week, which is to double up these calibration routines. So the idea there would be, we have the calibration data of like what errors there are at all of these measured positions. We have that, we apply that in feedforward to another round of calibration sampling, and then we basically add those 2 errors together. So we kind of superimpose those 2 sets, and we should get even more precise results. So it's possible that running this again, I'll probably do fewer poses next time, because I don't really like sitting around for 2.5 hours, because I can't really do any other work while it's going. Like, I want to pay attention to other things, but I also really want to be mindful of Jugglebot in case something is going weird, like the leg being tired. So I kind of like have to be just observing it, but it's so boring just sitting there like for like 2+ hours. So I'll probably do fewer poses, but it would be interesting to see if we can stack these calibration sets to try to remove some of this residual error that we're still seeing in here. Like, it's still not perfect. Like 7mm, I don't know. It'd be good to get that down to less than 5, I think. But that's fairly arbitrary, so yeah. Either way, it's very good. And now we don't need this mocap offset in catch dropped ball node. So this might seem like a very random point to note here, and it kind of is, and I'm only really aware of this because I just happened to try this at one point. But as evidence for the fact that this works really well, I think this is a very good demonstration of this. So let's have a look. We can go through our first demo of the day. Let me just get things up. So I'll just put you on, you don't need to watch me, but I'll put you back in the corner. Yeah, okay. So we can launch, yeah, something that's interesting that I don't know if I've actually mentioned before is that I have added in now an option to record or not record each juggling session, or each Jugglebot session, because my Rosbags folder was getting full of random recordings that I had not labeled, and I'm like, what the heck are these recordings? I'm never going to look on these again. So I now have a thing so I can decide in advance if I want to record the session or not. And I'll record this one, just in case something interesting happens. And this recording is recording the ROS messages. Okay, so we're all on. We don't need to home or anything because I was mucking around earlier today. We want to activate the robot. Up it goes, nice and snappy. And yeah, actually on that snappiness, one note for when the leg was being tied is that leg 4 was making that activation process not snappy. Like you could, just then I wasn't watching it, I could only just see it in the camera, so I wasn't watching too closely. But it should have just gone up with all legs at the same rate, up, stop, that's it. But when leg 4 was being sleepy or being tired, the platform would kind of raise up and then all the other legs would get there and then leg 4 would come up. So it would be like, and then tilt to get into the proper position. But it's all good now, so we don't need to worry about that. And we want to go to catch dropped ball node command. I need to work on my naming scheme. Catch dropped ball node command. Alright. So you may remember this is the one that follows the ball around, and it should detect when the ball is dropped and then catch that ball, but I am not using that stuff right now. I just want to use this as a demo to show that I can move the ball around and it tracks the ball very, very, very accurately. So I won't be able to talk much because the microphone is far away, but hopefully you get the idea. That one. So I've got to hide the ball before we get there because otherwise it goes a bit crazy. You see, as I move around, it's very good at tracking. Let me... Oh, it's down. But I should be able to drop, and it lands like straight in. So this is with no offset anymore. Pretty good. So you may remember that in the past, I needed to have an offset. I had a manual hard-coded offset in there of like 70 millimeters in the Y and 3.5 millimeters in the X or something like that. It might have been reversed, but I just had to have that offset because it just was never going to where it should go. But now that offset is 0 and it's looking at where the ball is and then projecting that down and then finding that XY coordinate and then commanding Jugglebot to be at that XY coordinate, and it just works. It's so good. It's such a relief. It's so nice. Although something that is very interesting is that you may have noticed then that in some instances the platform rotates a bit, and that's not kind of this catch dropped ball node is trying to keep the platform horizontal. Well, it's in its commands, it's never commanding any angle of any sort because it doesn't need to go on an angle if I'm just dropping the ball straight in. So that angle is only arising because of the calibration data that it's grabbing is saying, oh, you need to apply some angle offset to compensate for the error that should be there, which is not there. But yeah, so that's interesting, is that sometimes it does angle just a little bit when it's not supposed to, but it's not by much, and it doesn't seem to make much of a difference. So yeah, I'm very happy about that. Very, very glad to be rid of hard-coded offsets because they're a bit sketchy. Okay, a quick aside, I guess, is that I have a small update on the memory of the Jetson. So I realized in the stream last week how much of my memory of the Jetson's memory was being used on something, and I've had a little bit of an investigation into this, and it turns out that the VS Code SSH, so that's what I use to essentially just copy code to and from ChatGPT into the Jetson computer, and Plot Juggler also, both of them use a lot of memory. I don't know if it's always the case, but at least when I had them on and then as soon as I turned them off, there was a 1 gig difference in how much RAM was being used on the Jetson, which seems like a lot for these two applications. But yeah, I don't really know what it should be, but I don't know, a gig seems like a lot. And this was actually so much RAM was being taken up that during that 2,500 pose calibration routine, the Jetson actually completely froze. And I was a little bit worried that I'd have to do the whole thing again, because it only saves the file right at the very end of the session, so it has to finish in order to save. And I was really worried that I was going to have to do it all again when it froze. But thankfully, closing VS Code on my Windows 10 PC cleared the freeze, and then it just kept on going. And so when this froze, like, Jugglebot just was just out of pose, just waiting for the next command, but the Jetson had no command to give, so the robot was just stuck, and everything was stuck. Like, I could move the mouse extremely slowly on the Jetson, but as soon as I closed VS Code on my Windows 10 PC, the Jetson, off it goes. Happy as Larry. So that's a bit weird. Yeah, so I don't really know what to make of this. I don't know. SSH is something that I use all the time. Plot Juggler, I was previously opening Plot Juggler as soon as I opened the computer, essentially, and it was just open in the background all the time. I'm now only opening it when I need to, which does mean that I'm using it less because it's a bit less accessible. So it's a little bit annoying, but yeah, it's kind of a fix. I don't know, we'll see. But yeah, so it's a little bit of an update, but still, like, there's still a lot of memory being used. So like right now we're at like 5 gig, and I don't really know how to read this information too clearly. I had a bit of a talk with ChatGPT about it, but I don't know. It seemed like it was going to be a lot of work to get to the bottom of what else is taking up a lot of memory. But it seems like VNC is a very large part of it. Like if I make this bigger, as far as I'm aware, not VNC, VS Code. It seems like VS Code is a lot of these things. But I mean, right now I've got SSH is closed, but VNC is open, which is not normally open, and I've got 5 gig left. Or 5 gig taken, 2 gig left. Which is obviously enough to do what we just did. So, yeah. I don't know, computers are weird. I just wish I could have like unlimited computer resources. It'd be so nice to not have to worry about it. But maybe one day. Okay, I also have a quick update on how I am handling things in Mocap. Because now that we can position Jugglebot to be at an accurate pose, so not just position, but it can actually angle as well, I was thinking what the next step might be. And in the last stream, I mentioned that one of the next steps would be dynamic pose calibrations, so that way we can send Jugglebot not just one specific pose, but we can send it an entire trajectory to follow, and it should be able to follow that and keep the error at any given pose along that entire trajectory fairly low. And I'm still very interested in doing that, but I wanted to do something else instead. So as soon as I realized that this orientation thing was working, I was like, hang on, there's not really anything stopping Jugglebot now from being able to shoot hoops. So I really want a Jugglebot to be able to throw into my little cone catcher thing here. So I've got a bunch of motion capture markers on this printed part, and the idea is that I can have this somewhere, like I can either be holding it or I can have it fixed somewhere, and Jugglebot should be able to throw and have the ball land straight in the cup. I was like, oh, this is going to be fun. So I made this piece. I made a rigid body in QTM with this, and then I realized that it's going to be a little bit of work to get this data out to, like the data of where this rigid body is, out to the Jugglebot computer. So what I've done is I've had a small change to how I'm handling the rigid body data from QTM, where now all rigid bodies have their own topic. So as soon as I make a rigid body in QTM, so let me show you what that looks like. So here we have QTM, and we can see in the viewer here, we've got the base rigid body and the platform rigid body. And we also have, when I introduce it into the scene, let me zoom out a bit so we can see, we have the catching cone rigid body. So as I move this around, you can see its triad moves around as well. And I really need to get better with my randomizing points because I was like, oh yeah, this is pretty random, but it's not really, because if you take a center line through here, the points are very close to being perfectly mirrored around that line, which I didn't realize until I'd already made it, but whatever. It's pretty close. And so we can, yeah, it usually doesn't stuff up and gets the coordinate system correct. Although you can see it's kind of flipping around a little bit here as it sees and unsees different points. But anyway, as soon as I make a rigid body in QTM, that rigid body will get its own topic in ROS. And that topic is titled, whatever the name is in QTM, pose mocap. So now I can just add as many rigid bodies as I want in QTM, and that data will just go straight through into ROS, and I can just grab it from this topic, from its own topic, which is very handy. Previously, I was only publishing the platform pose. I wasn't even doing anything with the base pose or this pose because it didn't exist. But now, because all of this information is just being broadcast anyway, I figured I can use this information to figure out if the Jugglebot has moved since I last ran it. So you may remember that I have configured my motion capture system to have Jugglebot's origin, which is this dot here, be smack bang at the global coordinate system. So that way, any object that I'm tracking, if I've got a ball in here and I throw the ball around, that's going to be in Jugglebot's base coordinate system. However, Jugglebot can move if I kick it. Let's drag it over there. So now Jugglebot is off, but QTM hasn't realized this. And so what I'm doing now is, if the base has moved by a certain amount, and we can see what that amount is in the top left up here, we can see the 6-degree freedom data for each rigid body. So the base is now at 32, 15, and 1.3. If that error, if the base position is far enough away from just like 0, 0, 0, 0, 0, then we can be pretty sure the Jugglebot has moved, and then we can say all of our motion capture data is now invalid because the whole robot has moved, so the whole coordinate system is off. And I was thinking, this is a great idea because this will warn me to whether or not I have to reset it, which I can do pretty easily. I just go in here, transformation, fetch, okay, yes, and now it's fixed. And now we can see the base is right at the origin. So I wanted to have a system to kind of warn me to when I needed to do that. And I was like, okay, cool, I can set this up the way that I just described, and it should do exactly what we want. However, it's giving a lot of false positives. So as the robot moves around, I believe this is largely because I have a carpet in this room, and because Jugglebot is so damn heavy that as the platform moves around, it shifts things just a little bit. And also as markers on the base become blocked and unblocked, the rigid body that makes up the base changes just a little bit. So I can show you on here. So right now that rigid body looks super solid, and we can see that the 6-degree freedom coordinates are pretty much 0. But as I move around, you can kind of see that shifts a bit, especially when I walk past, because I'm blocking several cameras at once. So like actually just blocking one doesn't really change it too much, but it does shift just a little bit. And yeah, with the tolerances that I had, where I was saying if the base has moved by more than 5 millimeters or is more than 2 degrees off of vertical, then we say that the coordinate system is invalid, and then we should shut down, end the session, we need to reset. But that just kept happening. As markers were getting blocked and unblocked, it just kept giving false positives, and yeah, it was a bit too sensitive. So I like the idea of this, but I need to figure out a better way to tune it. Probably a very good way is actually to have a low pass filter where when these markers get blocked and unblocked, especially if it's as a result of Jugglebot moving around, that blockage is probably going to be fairly brief. So actually I probably should add a low pass filter and basically say, like, if the base has moved away from 0, 0, 0 for more than some amount of time, then we can say that it's invalid. That's probably a very good idea. If you have any other ideas of how to do that, perhaps more efficiently or better in any way, I would love to know. But yes, as I was doing it right now, where it's just like, as soon as we get any data that suggests that it's wrong, then shut down, that was a little bit too sensitive. And also, it's a little bit overkill, potentially, because this is updating at... The mocap data is coming into the Jetson at 300 Hertz. I need to double... Let me just quickly check this. I believe I am sending that out, yes, at 200 frames per second. So it's not actually 300. So at 200 frames per second, this data is coming in, and that node, which is the CAN handler node, which is the node that's kind of doing a lot of other stuff, or the CAN interface, I've changed it recently. I don't know, 300 Hertz feels a bit excessive for this. This could realistically be going at like 2 Hertz, just to check if the robot has moved. And I don't really know how to change this. So it would be good if I can throttle the subscriber, but I don't really know how to. So this, because I have this set up the way that I have, all rigid bodies have their data published as soon as it comes in. So it comes in at, well, that's actually not true. It comes in at 300 Hertz. At 200 Hertz, it publishes data if there's new data to be published. I could add a little filter in that publisher to say if the rigid body is base, then only publish more slowly. Or can I filter, like, can I throttle the subscriber? I don't really know. I don't know if throttling the subscriber is possible. I think throttling the publisher is probably better. Again, open to suggestions. Yeah, there's a lot about ROS that I still don't understand very well. Alright, so all of this has been kind of how you going. But the big question is, can Jugglebot sync hoops? We have a hoop, we have a Jugglebot. Can it sync it? Let's find out. That one. Alright, so let me position the hoop. I've got a little clamp on the wall to hold it. And let me just double check that its coordinate system hasn't inverted. Let's look on here. You can look with me. Yes, that looks correct. So yeah, that looks like where I put it. And you can hopefully, yeah, you should be able to see it just below me in that shot in your viewer now. Okay, so we want to start Jugglebot up. I will record this again, just in case something interesting happens. Actually, Jugglebot needs a ball. Alright, we are on. We can activate. For some reason, my messages don't publish sometimes. I've mentioned this a while ago. And someone did give some suggestions, but it's hard to... I gotta like dig deep into what's going on with the messaging here, and I'm not really that motivated to do it. I'm more keen to just like send it several times until it works. There's lots of weird things with this system. Alright, so we've activated. Let me, you can see what I'm doing. And I'll get rid of me so you can see my full code. I can't remember what this command is called. So let's look it up. In the Yasmin state machine, we want the hoop sinker. That's it. I love my naming. Very clear. Hoop sinker command. So this will activate that node of the state. I'll show you what I'm changing here. My god, I have too many windows open. Okay. Alright. So this is what I was just changing then. So we've got this mega state machine that is not really showing very well. Okay, this is a bit not effective. got too many nodes now. Okay, but we've got all of these nodes in our state machine, and what I just sent then, the hoop syncer command, was telling us to go from the standby active, which is down here, up to the hoop syncer. So now the hoop syncer node is active, and we are ready to attempt to sync some hoops. So let's go back to here. We can... Actually, no, you don't need to see that. You can just see Jugglebot. I always forget my code, my commands. So we've got a first command is to prepare the platform for the throw. So what it's doing right now is that it's constantly... Actually, I can show you, yeah, in this code. You can see up in this viewer in the top left, we've got a plan. So this plan is telling us what the proposed trajectory is for the ball to follow in order for it to be sunk in the hoop. So our plan is to have a roll of 1 degree, a pitch of negative 12 degrees, a launch velocity of 4.43, and some various stats on the throw. And so you can see, I'll move the hoop around, and you can see this updates as the hoop moves. So now our pitch and roll commands are being different, and if I raise the hoop up, we need a higher launch velocity, versus if I bring the thing down, we need a lower. And if I completely remove it out of the scope, then we have no throw plan because there's nothing to throw to. So yeah, hopefully you can... I should have had me in the shot then. But yeah, you can believe me that this is updating in real time and can work for any hoop position. So let me just put that back in so I don't need to hold it. And we have our plan. Again, it's pretty much the same as what it was before. So we can move the platform for throw. And I'll run that. There we go. We are now angled. That looks pretty good to me. Let me move. So many things to manage. I can't wait for AI to get to the point where I can just give it command of my cameras and it will do the cameras for me. Like, that looks pretty good. That looks like if that throws, that's going to go in the hoop. I'm hopeful. So now I don't want to move the platform for throw. I want to execute the throw. What do we need? That one. What is it doing? Alright, the Jetson has been a bit slow right now. Okay, there we go. So now I will send that service call right now to execute the throw, and we'll see what happens. Nothing. Okay. So the first thing that it does, the first thing that the hand does is it moves down to the bottom of its stroke, which it already was at, pretty much. But if it doesn't quite get there, it times out. So I'll resend it again. And what was that? Limp. Limp as. Let's try again. I was really hopeful this worked. I've done this probably like 30 times and it hasn't worked. But you never know. Maybe the stream is the time. We'll give it the 5 goes because I got 5 balls on my desk. But then I've obviously got some things to say about this. Whoa! That was very close. That was very, very close. Although the angle did seem off there, it kind of hit the handle of the hoop. That was also pretty close. But you can see that the hand is being very weird. I'll zoom into the hand on this camera. There we go. Alright, last one. Let's go. In the hoop. Is it even going to go at all? Oh. Limp. What was that? What was that? Alright, let's shut that down. So there's obviously some weird things happening. I'll collect the balls later. Yeah, so can Jugglebot sync hoops? Not yet, unfortunately. But that's okay. We're getting there. So what's going on? So before we talk about what the problems with this are, I want to just describe what's actually happening with this system. And I kind of did before, but just to go through it a bit more thoroughly. We start off by detecting the centroid of the catching cone, and that's actually calculated in QTM itself. So QTM detects these 5 markers, and then I have already told QTM that those 5 markers correspond to this rigid body, and I've also told QTM where one of these points is, specifically this one, in relation to the origin of that rigid body. So you may remember that you can, in QTM, you can translate and rotate rigid bodies. So I have translated this rigid body so that point, whatever it is, 3 or 4 or something, has these specific coordinates. And I got those coordinates from Onshape, because this was obviously CAD modeled, and I can just take the dimensions from the CAD. So this QTM figures out the origin of this rigid body, and then that origin is what's being sent out over the that topic. So this detecting the centroid is done in QTM. We're ignoring its orientation, just for now, just to simplify things. We then calculate the throw trajectory such that the origin of the platform is at x and y is equal to 0, so it's not translating anywhere at all, and z is 165, which is what I'm using as like the juggling plane right now, and that's the plane that all of the calibrations and everything were done at. We also have it set up so that the ball will peak 50 millimeters above the top of the catching cone, because otherwise, like if the ball peaks at the catching cone, then it's probably going to hit the edge of the cone and not actually go in. We want it to go up a little bit before going in. We have limits on the roll and the pitch of the platform, and we have limits on how fast the ball can be thrown. We then orient the platform for the throw, as you saw, and then we throw. And then the ball goes in theory. All of this code is in hoopsinker node.py, which is in the description, I'm pretty sure. If it's not right now, then I'll put it in after the end of the stream. Yes, so this is the general idea. There is a step before all this that I actually forgot about when I was writing this up, which, as we saw, is to get the hand to go down to the bottom of the stroke. Because the trajectory that gets generated when we throw is assuming that the hand is already at the bottom. So we need a step at the very beginning. We have step 0 is move to the bottom of the stroke. And that sometimes times out, as we saw. I believe the reason for it timing out is related to the really juddery, limp throws that Jugglebot was just making, which we will talk about in just a sec. But before that, I want to just have as an open question if anyone has any ideas for how to do this throw trajectory better. Because I started off, when I was first thinking about this, I was like, okay, Jugglebot is free to move around anywhere on this plane and to orient itself. So it should be able to get in a position, like, we really have a lot of choice here about what we want Jugglebot to optimize for when it's making this throw. We are assuming that the catching cone is in a static position, that it's not going to move once, like, the throw has been made, at least. So we have a target position that we want to throw the ball into, and we've got a lot of choice about where to be to make that throw. And I don't really know what the best choice would be. This criteria that I described just now is just what I ended up coming up with after trying a couple different things. But it would be cool to have Jugglebot be actively finding an ideal pose so that, for example, the launch speed is as low as possible. Because having a low launch speed would be nice to not have to wear out the hand motor, or not have to operate the hand motor as intensely if it's avoidable. So there's a lot of freedom with how to set up that trajectory, and I'm very open to suggestions on how to do this at all differently. But yeah, this is what I'm doing right now. So there's obviously a problem with controlling the hand, and I believe this problem is timing related. So the process that this goes through is that there is a node. In this case, it was hoop syncer node that generates the full trajectory of how the hand needs to move. That's at 500 hertz. That generates that full trajectory, and then tacks that onto the current, and that trajectory starts at like time is equal to 0, which doesn't really mean anything for ROS. So before that message gets sent out, all of the time aspects of that command, of that trajectory, are basically added to the current time. So we generate the full trajectory at 500 frames per second. We add the current time onto all of the timestamps, so that way the whole thing starts right now. That then gets sent out to the CAN interface node, which then receives that full trajectory list, and then it has a loop, essentially a loop, that says, is it time to publish the next command? If so, then publish it, and then remove it from the list. And then we go through again, like the next time the timer is called, it's not actually a loop, it's a timer. But the next time that timer goes, which is at 1000 hertz from memory, I'm pretty sure, we say, is it now time to publish the next one? And if it is, then we publish the next one, and then we delete it from the list, and then we just keep doing that until all of these poses are published. Sorry, all of like the position, the velocity feed forward, and the torque feed forward for that hand motor, they should all be getting published at 500 hertz as soon as the throw starts. That's obviously not happening though. I've tried a couple different diagnostic processes to try to get to the bottom of this, but none of them were really that high resolution. Like I was using the ROS topic hertz thing, where like it spits out how often messages are getting published over the topic. But because this trajectory is such a quick burst of messages, and the ROS topic hertz thing only goes like every second and just like averages over the last second, it wasn't really giving a very accurate representation of what was happening in that like 100 millisecond burst. I do have a CAN logger on like in the network that I could use, but that involves getting out another separate computer, and I don't really love that interface. It's very hard to understand, I feel. But in any event, I'm fairly sure the problem is somewhere, I don't know exactly where it is, but I'm fairly sure it's somewhere in the pipeline of generating the poses, the trajectory list, sending that trajectory list out to the CAN handler, and then the CAN handler sending it out to the CAN interface sending it out to the actual robot. This is the same CAN interface, mind you, that is doing a whole bunch of other stuff, like controlling all of the other legs to move to where they need to be, and also is right now doing that base, like making sure that the base is at the origin 300 or 200 times per second, as well as trying to publish these messages 500 times a second. So I kind of feel like I'm just overloading that one node and giving it too many things to do too quickly, especially very timing sensitive things. So yeah, I feel like it's just too much going through at once. So how can we improve this? Well, how about instead of using the Jetson computer, which has a lot of other tasks to handle, especially that one node has a lot of tasks to worry about. It doesn't need another 500 frames per second of data to process and send out to the CAN bus. What about using the other, like what 20 years ago would have been like a supercomputer, which is the Teensy, to do these calculations? And mind you, the Teensy right now is not really doing anything. I have set up on the robot an inclinometer, which measures inclination, and the Teensy was supposed to be a way to get that inclination data out from the sensor onto the CAN bus for the O drives or for the main computer to use. I actually don't think that inclinometer is really going to be very useful anymore. I haven't done anything with it in a couple months, and now that I've got this motion capture feed forward system in place, it's kind of made the inclinometer a bit redundant. The inclinometer will definitely give more accurate readings for inclination, and it could be useful in that regard, but I will still need to recalibrate its offset with respect to the platform's y-axis as well. So I don't know. I'm going to leave it on there, no doubt, but I don't think it's really doing much. So yeah, the Teensy is basically just sitting there, not really doing anything. It's probably using like less than 1% of its CPU, just kind of chilling. So what if we move the trajectory generation and the publishing to the teensy? And I don't think that the transmission time of the CAN signals is really going to be much. I asked ChatGPT about this, how long it would physically take for the message to go from the Jugglebot computer out to the hand motor, and it was something like 10 nanoseconds. So I don't really think that's that big of a problem, but the teensy is literally like 5 centimeters cable length wise away from the hand motor. So it's like physically right there. So if anything is going to send messages to the hand motor in a quick way, it's going to be the teensy. Not to mention, I'm fairly sure that the teensy has a real-time clock on it, so it can actually keep in sync and make sure that these messages are getting sent out at exactly the right time. But the question is the teensy fast enough to do this? Can the teensy generate that full trajectory really fast? And also, how fast is fast enough? To answer this, the second question of how fast is fast enough, I have, this isn't really answering the question per se, but it's giving us like a ballpark figure of how much time is involved in the different parts of this, of like the juggling process. And I've got data here of me juggling 5 balls, which was a pretty clean run, I think. It's pretty decent. It does loop as well after 16 seconds, so it's not like an infinite run or anything, but it's a decent run. And what we can do, what is that button? Let's not do that. I don't know what that is. But we can look at the trajectory of one of these balls, and we can see what it's doing throughout its path. And I really like this interface. This is so nice. Whoops. So let's go back to here, and I want to see how long I'm holding the ball for. So we can, whoops. We can see, oh my god. The ball goes up, and then it comes down, and somewhere in around like here-ish, I catch the ball, and somewhere around here-ish, I throw the ball. And it's actually surprisingly hard to see where I actually catch and throw the ball, just by looking at the ball in the viewer, even from the XYZ plots. And it's a little bit annoying because I'm not perfectly, like, I don't know, I'm very messy when viewed from above in this recording at least, and probably in general. Like you really, just as a general idea, if you're into juggling, you really want to stay as flat as possible. So this is, I don't know, it's very interesting to see this. I would have thought I'd be a lot more flat than this. But yeah, it makes it very hard to see where I'm actually catching and throwing the ball. But I'm going to, my best guess seems to be like this period in here. Because the Z direction is changing from falling down to being thrown up. The X is doing this weird, like as soon as I release it here, then it has like a fairly constant position. And oh my god, keep unclicking it. Yeah, and like that kind of tracks with what makes sense. Like as I pan through, it's like, yeah, catch like here, and then throw. Yeah, you can see there's a bit of like a jump where I kind of flick it with my fingers, I guess. But it's around that long. And that's 0.24 of a second. So 240 milliseconds is how much time I'm holding the ball for. And that is obviously not like, I don't know, the most important aspect of the timing here, but it's like, it gives some indication of how much time we have when juggling 5 balls. And that's like, yeah, the ball's in the air for a lot longer than we're holding it for, and we've got 240 milliseconds while we're holding it to figure out what we want to do next. Even though it doesn't really work that way, but it's like it's a ballpark. But how fast is the teensy? Can the teensy generate the full trajectory of what we're going to do next within around this ballpark? I don't know. Let's find out. I do know, and you will know too. Soon, very soon. So I've got this code. I have a second teensy over here because I didn't want to muck around with the one that's actually on the robot just yet. But this is exactly the same teensy 4.0. This has nothing else running on it, so it's possible things will change once I actually get it operating properly. But I think you will agree that it's pretty fine. So I've got this set up where I can generate either the throw trajectory or the catch trajectory or the full trajectory if it is throwing, waiting for the ball, and then catching the same ball that it threw. So let's look at the full trajectory. And we want to have a throw velocity of, well, let's see actually, when we were getting Jugglebot to work just then, when it was trying to shoot hoops, Let's ignore all of this stuff. We had a throw velocity of 4.43 meters per second. So let's have a look at that. What have I opened here? And we have a plot that always generates behind all my other windows for some reason. And yeah, this is what we've got. So we've got the full trajectory. We have position in revolutions, velocity revolutions per second, and the torque. So these are the three commands that are going to be sent out to the O drive to move. This is generated in 88 microseconds, and it takes up less than 1% of the CPU of the Jetson. That's pretty damn fast. This means that we could catch the ball, while catching the ball, figure out where we're going to throw next, and then generate the full trajectory from wherever we are right now in like this stage of the catch, and then have the plan for where we're going to throw done before the ball has even reached the bottom of the hand stroke. That is so good. Like, yeah, I'm very, very happy about this. There are some weird things that happen though. Like if I generate the full command, the full path, but we have a really, really low throw velocity, like 0.1 meters per second, then it's a bit less. This is all also just being sent over the serial interface, so it's a little bit sketchy. Like it drops messages every now and then. Obviously the real one won't, so that's like all of these big spikes are just because messages are being dropped because it's sketchy serial. But we can see weird things happen. This one takes 500 microseconds, and when I first saw this I was like, oh no, like is this, and it takes up 5% of the CPU, like oh, this isn't great. I don't really want it to be taking that long and taking up that much of the processing power. But then I realized that 0.1 meters per second, if you're throwing an object where it leaves your hand at 0.1 meters per second, it's only going to raise by 2 centimeters. So that's not a throw that Jugglebot is ever going to make. And it doesn't even really make sense to make that throw because I'm fairly sure the hand will reach, like it'll catch, the ball won't even really leave the hand at all. So it doesn't make sense to have that be a thing. What would more likely be the case is if we're generating a throw trajectory with, what did we have before, 4.43 meters per second, we can generate that trajectory in 24 microseconds. Boom, we generate that, we tell the hand motor to follow this path, and it just throws, in principle. So you might be able to gather that I'm pretty keen on this idea. However, it does go against this unification plan that we were kind of talking about a little while ago, where it would be good, it feels like the right move long term to have the platform and the hand operate in a coordinated manner. So right now, my thinking is that the platform just moves along this plane, and it can orient as well on that plane, and then the hand is what's doing any of the catching and throwing. So if the ball's coming in, the platform just moves to the side to intercept that catch, and then the hand does the actual Z motion. However, the hardware would be fully capable of having the platform handle some amount of that Z motion as well, so it can be like an even softer catch, and that can give us even more time to throw the ball. So if the platform moves up at the same time that the hand is moving up to throw the ball, we can get a kind of compounding effect where we can throw the ball even higher than we would be able to with just the hand alone. And same thing with catching, we can have the catches be even smoother if the platform also moves up and down to help with that motion. I think that's definitely where we are headed, but I think it's worth taking a step back and simplifying things just a little bit for now, like minimum viable product style, to just get things to work. So this is going to have the hand is operating completely separately to the platform. The platform will just go to where it needs to go, and then the hand will handle its own trajectory just separately by itself, like on a completely separate computer as well on the Teensy. This does also, there's one biggest drawback that I can think of for this is that it requires that the clock of the main Jugglebot computer is very, very closely in sync with the clock on the Teensy. Because, as I mentioned before, these trajectories are only ever generated with time starting at 0. So it needs we need to know when to actually begin making that throw. So what I'm thinking of doing here is having the Teensy code generate the trajectory so that time, rather than starting at 0, it starts at some negative time where 0, according to the trajectory, is when the throw is actually made. And we can know when that is from the plot. So let me just generate another plot. What do we do? Let's do the full and the same let's go 5 meters per second. And the plot's down the bottom. So let me draw on this. So it should be, like, if you're just looking at the position plot, it's kind of hard to tell when the ball might be thrown here. But if you're looking at the velocity plot, it's pretty clear that as soon as the velocity of the hand starts to go back down, then the ball is going to continue with whatever this peak velocity is and keep going. So the idea here is that the ball will depart here, fly, and then land in the hand right then, when the hand is going back down at that velocity. So what I'm thinking of doing is having the trajectory generated so that we tell the Teensy, I want to throw with this much launch velocity. So that's currently what I'm doing. Whatever the launch velocity is, that's it. And then also have it set up so that the 0 time is at the actual time when the throw itself is made. And that way, when we want to make a throw, all we need to do is tell the Teensy, hey, right now it is, I don't know, it's been 1 minute and 30 seconds since the session began. At 1 minute and 32 seconds and however many nanoseconds, you need to make a throw with this much launch velocity at exactly that time. So the throw is made at that time. And I think that if we can get this to work, that is a huge, huge step. Like, that's very, very, very close to being able to juggle, like either with itself or with me. If we can make the robot follow a throw or catch trajectory so that we can just tell it, there is a ball that needs to be thrown at this exact time with this much velocity at this angle, make that happen, and then the same thing with the catch. That's all juggling is. If you can make the throw and you can make the catch, you just string them together and then you're done. In theory. So yeah, I'm very hopeful about this, but it does require that the two clocks are very, very closely in sync. So I am not 100% sure how to do that, but I kind of feel like it can't be that hard. This is something that several people have mentioned in the past as being something that is non-trivial to do, but I mean, so is the rest of this. So I kind of feel like it should be doable. Yeah. So I'm pretty keen for that. I have high hopes. I have very high hopes. I think that shooting hoops, as soon as I get the Teensy to do this, I need to, there's obviously a little bit of work involved here, like getting those clocks to actually be in sync, so that way when we tell it to make a throw at a given time, it agrees on what that time actually means. But yeah, I think it should work. I'm very keen. All right, that's a lot of rambling. I think that's all to mention. As always, it's probably little things, but we'll get there when we get there. And yeah, as always, if you have any thoughts at all, I would love to know. It's been an interesting week. There's lots of different things going on. There's so many different little aspects that I can go down, and I've constantly been thinking, like, I would love, because I keep forgetting all of my ROS commands, I would so love to just spend a week to remake the Jugglebot GUI, because you may remember the last one, which is functional and it works, but it's a bit kind of clunky and crap. This is it. And like, this is cool, but like, for one thing, it's not actually like relevant anymore. Like, it doesn't actually interact with my current code anymore. This was built to interact with my last version of ROS code, so I would need to completely change how this is working on the back end. But also, I think it could definitely be spruced up a little bit. Like, one of the things that I want to include is I've got this message of the robot state being published with some frequency. I can't remember. It's 100 or 200 hertz. of what is going on with all of the motors. And I would love to just have like the little plots. I can just imagine like a really nice interface that shows really clearly what's going on with all of the motors, with the whole robot setup. Like, yeah, I really want to make that, but then it's just kind of like a bit of a distraction from everything else. It's very hard to put those desires aside to focus on sitting in front of the robot for 2.5 hours waiting for it to go through its calibration sequence, because one of those is definitely a little bit more important than the other. But we'll get there. Yep. Cool. All right. Well, I hope you found that interesting, as always. And as always, if you have any comments at all, please do let me know. I know that I'm very bad with responding to comments, and it's taking me a while to do that, but I do read them all. I have read all of the comments that I haven't replied to. I'm fairly sure. I just haven't replied to them yet. Yep. Life gets in the way. Yep. Yep. All right. That's enough. I will have a stream next week. I have checked my calendar. I was good this week. And yeah, so until then, I hope you have a good one and good luck with everything that you're doing.